Welcome to Highline BI 348 class video number 51. Hey, if you want to download this work with BI 348 Chapter 4 or the PowerPoints, click on the link below the video. Hey, we got to talk about hypothesis testing for our slope and intercept our test statistics. Now, we're going to look at a few PowerPoint slides, so I'm going to hit Shift F5. Statistical inference. That just means we take a sample from the population, calculate a statistic that estimates a population parameter, and then from sample evidence, make reasonable statements about the population parameter. Now, in our prereq business 210, we did hypothesis testing and confidence intervals. Now, let's go to our next slide and talk about inference and regression. Now, in regression analysis, we took a sample and estimated the parameters for slope and y-intercept. The sample statistics for slope and y-intercepts are our point estimates of the population parameter, slope and y-intercept. So now, with inference, hypothesis testing in particular, now we need to test to see whether our point estimate, slope and y-intercept, are reasonable or not. Now, before we can test the reasonableness of our slope and y-intercept, we must check to see if the assumptions necessary to use our least square regression model are valid. Now, we talked about this earlier in this chapter. Let's go to slide 75 and look at the three assumptions. Now, this is a drawing we saw earlier in the class that describes the distribution of error values around our regression line. And one of the assumptions is that it has to have a bell-shaped distribution. And this sort of makes sense. If this is going to be a good line for predicting, then as we get further and further above or below, it's less and less likely that there'll be a value. Remember, if this is going to be a useful line for predicting, then most of the values will be clustered around this line. So the first assumption is normal distribution. The second assumption is that the expected value of epsilon, or error, has to be 0 and sits exactly on the line. And that sort of makes sense. If there's some values above and below kind of evenly distributed, then the expected value should be 0. The third assumption we're going to have to test is that the standard deviation or the variance along this line has to be consistent. Now, there's a relatively straightforward way to check all three of these assumptions. If we go to slide 79, we've talked about residuals, but this is a residual plot. Now, the way you create this is these are the residuals. Remember the difference between the particular y value and the predicted value? But we plotted this against x. And what's so important about plotting it against x is that we have our experimental region, the min and the max. And so we want to look at how the residuals behave across the experimental region. Our first assumption, the error term epsilon is normally distributed, well, that can be visually checked out if most of the dots are right along the line. That means there's a higher frequency, and then they kind of tail off on either side. Then this assumption is met. Now, it doesn't look perfect here, but there's no strong violation of this assumption. The next assumption that the expected value of our epsilon error is 0, well, that can be visually checked out if, again, we have most of the markers right along the line, and then there's a bunch above and below. If we took the average at any particular point, it should be right on the line. And finally, our third assumption, a constant variance or standard deviation, that can be visually checked by seeing if there's a kind of an even swath all the way across from the min to the max. Now, you can see we have some spots where it kind of looks like that's not happening. There's some missing values here. But in general, there's no strong violation with this residual plot of our assumptions. So a residual plot like this, if we saw it, we'd go ahead with our inference. Now, the question, of course, comes up, what does a plot look like where we would violate these assumptions and not be able to move forward with inference? Let's go to slide 81. Now, this is straight from our textbook. This is a great picture. Now, in this case, we can clearly see the residuals start to tail off in either direction, right? They're supposed to be cluttered around the line with an even swath. That's evidence of a variance that is not consistent. This second panel here, we kind of have some residuals going up and then down. Here, the equation does not reflect a relationship between the x and y. Down here, we could see, well, wait a second. The highest frequency of dots should be right on the 0 line with some above and below, and that's not at all what's happening here. This is kind of skewed to the bottom here with some residuals tailing off. And finally, this one, this was to check independence. It clearly looks like if this was like quarterly sales data, there's clearly a pattern. Values seem to be related. Now, we didn't have a data set where we needed to check this in this chapter. So if you see any of these, then you're not going to move forward with inference. Now, back to slide 79. If we get a residual plot that looks like this, we can go ahead with our hypothesis test to test slope and y-intercept. Now let's go to slide 84. And here we want to ask, what is the logical element to test in linear regression? And of course, it's the slope. Because imagine here, slope, well, we clearly are going to get some number that's not 0. Over here, the slope probably would come out close to 0. So when we're testing whether there's a significant relationship between x and y, we test the slope. So if the slope is 0, we're going to conclude there is probably not a relationship. If the slope is not 0, there is probably a relationship. So it's slope that we're going to test. Slope is 0, there's not a significant relationship. Slope not 0, we'll say there's a significant relationship. Now let's go look at slide number 86. Here's our steps. There's 5 of them. Here's 3 of them. The first step in hypothesis testing, state the null and alternative hypothesis. So our null hypothesis is going to be either the slope is equal to 0, or if we're doing multiple regression, all slopes are equal to 0. The alternative hypothesis will then be either the individual slope is not 0 or all slopes are not 0. Now notice if we say all slopes are not 0, there could be a couple of them in there that are 0, but one of them is big and making up for the fact that there's a relationship. So what we will conclude is if we accept our alternative and we're doing multiple regression, we'll say at least one slope is not equal to 0. Now that's step 1. Step 2 is always picking our alpha. Alpha is the risk of rejecting the null hypothesis when it's true. Alpha will also help us determine the hurdle for whether or not the test statistic just represents sample error or there is a true statistically significant difference. That means it'll be past the hurdle. So in terms of alpha, I actually want to jump ahead all the way to slide 96 and remind yourself, jog your memory of what we did back in Business 210. Now, we did mostly Bell, shape, and t-test, but we had some other distributions. In testing for slope, we're going to use the F distribution. And here it is. Whatever the distribution, alpha will determine the hurdle. So alpha is 0.05. That's the risk of rejecting the null hypothesis, even though it's true. The rest of this over here would be 95%. So alpha will tell us what the hurdle is. If our F critical value is 3.08, when we calculate our test statistic from our sample data, if it ends up out here somewhere, then we reject the null hypothesis and accept the alternative. If it's in here somewhere, we fail to reject the null hypothesis. All right, let's go back to slide 86 because we want to continue talking about step 2 and alpha. So alpha will determine our hurdle, that line, right? Alpha is also used to compare against p-value. When we calculate our test statistic, there's 2 ways. We can do the critical value way, and we can also do the p-value way. And the p-value way is often easier. And we'll simply calculate p-value for that test statistic and compare it to alpha. If p-value is less than alpha, we reject the null and accept the alternative. Now, alpha is often 0.05 and 0.01. For confidence interval, that would be 95 and 99. Now, when we're testing the slope, when we accept our alternative, that means when we get a statistically significant difference, it will mean it is reasonable to assume that at least one of the slopes is not 0. Or, more importantly, it is reasonable to assume that there's a statistically significant relationship. That's step 2. Step 3, that's just the rejection rule. This will be our rejection rule. We actually already mentioned it up here. If p-value is less than or alpha, we reject the null and accept the alternative. Otherwise, we fail to reject the null hypothesis. Next slide gives us step 4. This is where we calculate our test statistic. Now, for calculating whether a single slope or all the slopes are equal to 0 or not equal to 0, we use the f-test statistic. There it is. Now, it's not that hard. Mean square regression divided by mean square error. We already calculated these. And then we would go ahead and calculate the p-value for those. We're actually not going to have to calculate this because we can use Data Analysis Regression feature, and it will spit out everything. However, for testing the individual slope, there's our formula. And for the individual y-intercept, there's our formula. If you want to do those formulas, and I actually have an example over in our Excel workbook, you can. Otherwise, we'll just use the Data Analysis Regression feature. In either case, when you're calculating t to test either the individual slope or the y-intercept, we're going to get a p-value for our t-test statistic, and there would be the formula for that. Next slide, slide 87, is step 5. If we reject the null and accept the alternative, we'll say the sample evidence suggests that at least one of the slopes is not equal to 0. It's reasonable to assume that there's a significant relationship at the given level of significance. If we fail to reject the null, we'll say the sample evidence suggests that all slopes are equal to 0. It's reasonable to assume that there is not a significant relationship at the given level of significance. These conclusions are for our slope. We'll talk about what to do for y-intercept when we run our data analysis regression. Now, let's jump over to Excel. We're on the sheet hypothesis test. And here is the example we've been using all chapter. X is weekly ad expense, Y is weekly sales. Let's go up to data, data analysis, regression, click OK. Input range for our Y, click on the top cell, Control Shift down arrow, Control backspace. Tab, the input for our X, click on the label, Control Shift down arrow, Control backspace. Now I'm going to select labels. Confidence interval of 99. Remember, confidence intervals spit out a 95. Or actually, this is the first time we're going to look at it. It'll spit out a 95 and a 99. We want our residuals and our residual plots. Of course, the very first step is to check our residual plots. I want to make sure that I'm going to put it in E1 and click OK. Now we look at our residual plot. And sure enough, it looks like over the experimental range, checking for normality, the normal distribution, most of the markers of the highest frequency is right on the 0 line. Consistent variance, it seems like it's more or less consistent. And then also for expected error value equal to 0, that also looks like it's OK. So our assumptions are met. Now we can go on to inference. Now here's the magic, of course. There's our F statistic. And there is an incredibly small number. When you see E minus 77, that means we have to slide this over 77 times. That is just a huge F. That is just an incredibly small p-value. So we would conclude, because we have a single x, we would conclude it's reasonable to assume that the slope is not 0. Further, it's reasonable to assume that there's a significant relationship between the x and y. Now we can look down here, and I'm going to add some yellow to this. And we can look down here at these p-values. Y-intercept, well, let's look at the weekly ad expense. Well, of course, it's going to be exactly the same because there's only one x value. So we come to the same conclusion there. That slope is not 0. There's a statistically significant difference. The p-value for the y-intercept, if we're testing y-intercept equals 0, Well, this is very small. This is less than 0.01. So we reject the null that the intercept is equal to 0. So therefore, it must be something other than 0, or we conclude it's not 0. And sure enough, that number is pretty far away from 0. Now, if we're using confidence intervals to check, if 0 is within the interval, then we fail to reject the null hypothesis. And neither at 5% or 1% do we get 0 in our interval. So we have confidence that both our slope is not 0 and our y-intercept is not 0. Now we want to go over to HT2 for hypothesis test 2. And we're going to run the same data analysis, regression. Click OK. It's remembering stuff from the last time we did this. So I'm going to click in D, Control-Shift down arrow, Control backspace. X, highlight. Highlight the 2 column headers, field names, Control-Shift down arrow, Control backspace. We have labels, confidence interval, residuals, and residual plots. Our output range, I don't want it there, so I'm going to highlight this and very carefully put it in F1 and click OK. So because this is a discrete variable, we get only markers at the individual numbers. And this is looking fine, right? Most of the dots look like they're right at the middle, and there's kind of a more or less even variation throughout. And it clearly looks like maybe this one's not quite 0, but certainly the average of all these are right at 0. I mean, not that one either. But again, there's no clear violation of our assumptions here. And then we look at our second one. Similarly, I don't see any clear violation as long as you kind of have more or less an even swath like that. And it looks like there are more values right at the center. We don't have any strong evidence to reject the assumptions. So we can go ahead with our hypothesis test. Here's our F and our p-value for our F test statistic. That is incredibly small. So we conclude at least one slope is not equal to 0, and it's reasonable to assume that there's a significant relationship. Now, if we look down for our sample statistics and the p-value. So for the individual slopes, these are very small p-values. So our conclusion would be that the slopes are not equal to 0. It's reasonable to assume that there's a relationship. However, for our y-intercept, when we get a p-value less than either 0.05 or this is a 2-tail, so we'd have to split it in half. Either way you go, whether it's 1 or 5 or 2.5, that's much bigger. So we fail to reject the null hypothesis. And the null hypothesis is that the intercept is equal to 0. But well, wait a second, that's minus almost 2,000. Well, look at the standard deviation. If you remember your distributions, because this is a t-distribution, we'd take the standard deviation, and to get 95%, that would be 2 of these. That would be 2,600 on either side. So this is actually within that region. You can look over here in the confidence intervals, and either one of these, either at 5% or 1%, both of them contain 0. So that means we fail to reject the null hypothesis. Now, what does that mean? That doesn't mean we can't still use this. Not only that, but for this particular example, this, and we did this one earlier, the experimental region, this falls outside the experimental region, so it is not of concern to us. However, we can still use it for our model over the experimental range. All right, hypothesis testing using the data analysis regression feature. That is awesome. Now, I do have a sheet here if you are curious. If you go to Formulas 2, and actually if we go back over to hypothesis test 1, this example here with all of these calculations, if you come over to Formulas 2, I've done every single calculation. And if you are curious and want to hunt through this, so every single one of the calculations, I always put the formulas off to the side. And if we come over here, okay, here's all of our calculations. Here's all the actual formulas. And we get down into here into our Data Analysis Regression output. Here's all the formulas, including every single one of these, the coefficients, the standard error, the t-stat, p-value, confidence intervals. Here's all the formulas, and if you open up any one of these, you can go ahead and see the calculations. All right, that is not necessary if you like using the Data Analysis Regression feature, then there you go. All right, so in this video, we talked about hypothesis testing and using Data Analysis Regression feature to test whether the slope or all the slopes are equal to 0 enough to test for significant relationship. All right, next video, we have one last video. I'm going to show you how to do similar calculations, but with the line est function. All right, we'll see you next video.